Welcome to the Walton Pi. Today I'm going to be talking about what it means for something to be a group. So, a group is a set of elements with a binary relation star which satisfies the three properties. One, it's associative. So A star B and then star C, that's the same as A star of B star C. So it doesn't matter the order that you do it for any A, B, and C in the set. Two, there's an identity element E, where for any element A in the set, A star E is the same as E star A, and that just gives you A. And then the third rule is for any A in the set, there's also an inverse A. A minus 1, we usually just call it A inverse, so that A star A inverse is the same as A inverse star A, which is just the identity element E. So we can think of a group as basically being addition in the integers. So the integers, we have 1 plus 2 plus 3 is the same as 1 plus, parenthesis, 2 plus 3. It doesn't matter the order you add them, it's still going to work. So it's associative in that way. We have 7 plus 0 is 0 plus 7 equals 7. So we have an additive identity, 0. And then we also have 7 plus minus 7, the inverse of addition, that gives us 0. So we have all those different properties in the integers. However, not all groups are as nice as the integers. But if you're trying to think of, okay, what does this mean? Like, the integers is a very basic example of a group that you can use to think about what does it mean. Okay. Now, let's talk about some not nice groups. Okay, so in the integers, we have a commutative property. That means 3 plus 4 is the same as 4 plus 3. It doesn't matter the order you do it. And so groups where A plus B is always B plus A, those are called Abelian groups or commutative groups. They commute, they go back and forth. It doesn't matter the order. And they're called Abelian. They're named after this handsome fellow that's pictured here. His name is Niels Abel. And so that's why these are called Abelian or Abelian. Everyone just calls them Abelian. But this property does not always hold in generic groups. For example, we have the group D8, which we'll talk about more later, but this is the group of all symmetries of a square. So why is this a non-abelian group? So if we look at a square, there are 8 symmetries of the square. So if we start with the 1, 2, 3, 4 labeled in the counterclockwise direction as labeled as our identity element, we can then see what can we do to that. So one option is we can rotate it. So if we rotate it once, the position that used to be 1 is now 4, and then what used to be 2 is now 1, what used to be 3 is now 2, what used to be 4 is now 3, and so we can rotate this square. And then we could rotate it again, so that's r squared. We've rotated twice. And then r3 is we've rotated it 3 times. And if we rotate it a 4th time, we're back to e. But there's also the symmetry where we could just reflect it. So D, we're going to say that we reflect it once. But then what if we reflect it and then rotate it? That gives us this dr element that we have here. If we do D and then rotate twice, and then D and then rotate 3 times, that ends up giving us all the symmetries of a square. Okay, so the proof as to why that's all of them, that's a little hard. Take a square, label it, and see if you can get anything that's different. Spoiler alert, you can't. And so these are the 8 symmetries of the square. And so why is D8 not abelian? Let's look at dr and rd. So dr and then rd. If we rotate and then flip it, we get 1, 4, 3, 2. If I read it in the counterclockwise, in the clockwise direction. But if I do d and then r, I get 3, 2, 1, 4, which is different than rd. So dr and rd are different. So the order we do those things matters. Okay, so that means that this is not a commutative group. It is still a group because it is still associative. It still has the identity and it still has inverses. But it's not going to be a commutative group. Okay, so let's summarize what we've learned so far about a group. A group is a set of elements with a binary relation where it's associative, where you have an identity element, and you have inverses. Okay, and then also, if we have a commutative property, so A star B is the same as B star A, then that is going to be what's called an abelian group. I hope this cleared up what it means for something to be a group. If this was helpful, please consider liking and subscribing. It really helps me out to be able to keep making these videos. I hope you have a great rest of your day, and good luck with all of your math.